Welcome to monochemistry. Today we're going to talk a little bit about heat transfers and how first of all, how they work and how we can use what happens in a heat transfer to kind of mathematically calculate different factors, okay, or different variables about the heat transfer. But also we're going to talk a little bit about why these heat transfers are important both in chemistry and in our everyday lives. Okay, so in this picture here, you see that I've got some this is iron, by the way. I've got some iron being heated up by this Bunsen burner, and I'm going to very carefully pick it up and put it into this cup of water. Now, don't worry, I didn't hurt myself when I did that. You've got to understand, and I'm sure you do already, but let's just talk about this. I think you would agree that the temperature in this area of the iron was very warm initially meaning when I put it in the water, and the temperature of the water was relatively cold. Okay, so what's going to happen? Well, the temperature of the iron is going to go down because of the water, and the temperature of the water is going to go up because of the iron. Okay? In other words, the heat lost by the iron is going to be picked up by the water. So watch this. The energy lost, the heat lost by the iron is going to be gained by the water. Okay? All right, now, we know what Q is. Q is a value, and this obviously involves a temperature change, so it's going to be mc delta T. But the key here is that the final temperature, the TF of the iron, is going to be equal to the TF of the water. And that should be a capital F. TF of the water. Okay, because they're going to reach a point where they're the same temperature. Okay, so the relationship between these, the energy lost by one equals the energy gained of the other. And that's why that negative is there, because the iron would be releasing energy, an exothermic process, and the water would be gaining that energy, which would be an endothermic process, and they would be equal to each other. So negative, the Q of the iron is going to equal Q of the H2O. And it's important to understand that the final temperature is going to be the same. Okay? All right, so that's the basics of what we're going to do here, heat transfers. The one thing loses energy, the other thing gains energy. Now, we can use that principle both to calculate it mathematically, like I showed you before. You could use mc delta T of the iron. Negative mc delta T of the iron is going to equal mc delta T of the water. But also, we can use that idea to measure the heat transfers, okay, using special devices called calorimeters. Okay, now this one here is what's known as a coffee cup calorimeter, and this is one that we will likely get some experience with this semester. We're going to do a lab that's called coffee cup calorimetry. Now, a calorimeter comes from the word from the two words calorie meter. Now, a calorie, the definition of the word calorie, is the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. That's what a calorie is. You've heard that word before, I'm sure you have, but that's the actual definition of what a calorie is. Now, unfortunately, calories are not the units that we use to represent energy transfers anymore. They're not. We use joules. But calorimeters are devices that can measure the amount of energy being transferred. Okay, so a calorimeter is a device that can measure the amount of energy being transferred. Okay, so measuring heat transfers. This is a coffee cup calorimeter. Okay, so in here, just go through. You might want to jot this down and label it. You've got your thermometer, you've got your nested cups, which means you've got one cup stacked on the other. Okay, and there's a reason why that happens, and I'll talk about that in a second. So you've got one cup stacked on another, you've got a lid. Obviously, we don't want heat to escape as much as possible. We've got a thermometer. so we can measure the temperature change. Makes sense. We've got a stir so that we can stir if need be. We've got a reaction mixture. This is usually like water and something. This could be something else. Okay? And we've got a nested, we've got the cups, like I said before. Now, this space right here creates a buffer between the external environment and the internal environment, and that's why it's there. It's a flow of oxygen or air in there, trapped air, that prevents the flow of energy out of the calorimeter. Okay? So, if I put some things in the water and they react together and there's a temperature change, then I can measure that temperature change. And if I can measure that temperature change and I know what substances I actually have already, then I can use the formula we talked about before, which is the Q of the reaction, in this case, is going to be equal to negative the Q of the water. Let me write that down. The Q of the reaction, or the heat gained or lost by the reaction, is going to be equal to, but opposite to, the heat gained or lost by the water inside the calorimeter. Okay? Makes sense? So if I have a reaction going on in here, I'm going to measure the temperature change of it. I know all of that information. I know how much water's in there. I know the C value of water. I also know the temperature change of the water. Bam, done. I can also then tell what the Q of the reaction was based on this based on this mathematical relationship. Okay, so this one here is a different type of calorimeter. It's a bomb calorimeter. Now, it's called a bomb calorimeter because it has a special compartment inside the calorimeter where the reaction takes place. Notice, or note, there's no water in here. So there's a reaction taking place in here. Okay, and the reaction happens. This is like a protective case for that reaction. Okay, this is an energy source for that reaction, so electrodes providing energy, heat, whatever needed. Okay, and then the reaction is going to happen and heat is going to be released to the surroundings. And that's going to allow me to measure the temperature change, which will of course allow me to calculate the Q of the reaction. Now, in this case, it's not going to be the Q of the reaction equals minus the Q of the water. It's going to be the Q of the reaction is going to be equal to minus the Q of the calorimeter. Okay, so when you use a bomb calorimeter, that's what's going to happen. So you would know the C value for the calorimeter, you would know the mass, you would know all of that stuff, and then you'd be able to calculate the Q of the reaction. Okay? All right, so let's just review, and then we'll talk about why it's important. So, like in the first instance, we have a hot piece of metal, we put it in water, that's the relationship right there. This is how we are going to measure, okay, Q of the calorimeter. Sometimes, if we're using like a coffee cup or something like that, the Q of the calorimeter is actually the Q of H2O. So the Q minus the Q of the reaction is going to equal the Q of the water, if it's a coffee cup calorimeter. If it's a regular calorimeter, you can use that. So this is a way to measure the heat transfer. Kind of cool. Over here, notice this is a little bit different. We have the Q of a reaction is going to be equal, or minus the Q of the reaction is going to be equal to the Q of water. And I put over here in brackets electricity production. Now, why did I do that? Well, electricity production is based on boiling water. Okay, so we burn something, we do something that produces heat. That heat is then transferred to water. Water then turns into steam, and steam turns a turbine. And that turning turbine is going to produce your electricity. Okay, so this right here is the key to producing electricity. So if you can understand this, and this, then you can understand how electricity is produced. Okay, so we burn coal. That coal is used to heat up water. That water turns into steam, turns turbines, and those turbines are then converted into electricity. The energy from the moving turbines, the kinetic energy, is used to produce electricity. Okay, and then that electricity runs to your home and allows you to watch this video, which I think is pretty cool. That, in a nutshell, is how heat transfers work. Make sure you write down your questions, and I'll see you in class.